Welcome to CJC Introduction to Probability and Statistics webinar. I'm Calandra. Today we're going to cover Module 1, Examining Distributions. The learning resource starts by giving you a visual of the big picture of statistics. So the first step when doing a study is to determine the population from which you want to get some information about. So first we're going to produce data. Once you produce data, you next need to analyze the data, come up with ways to represent it visually or numerically, and that step is the exploratory data analysis. Okay, once you have your data organized, you need to know probability so that you can eventually make inferences about the data and be pretty certain that the group that you studied is representative of a larger population that you might want to make a conclusion about. So in this module, we are going to start with step 2, where we want to be able to summarize the data that's collected in a meaningful and concise way. So first you need to know some definitions as we go through the course. A population is the group that consists of all persons about whom you want to make an inference. The sample is a subset of the population, and these are the folks from whom you are actually collecting data. So from that sample, you want to make an inference that your findings apply to the population. Data are information collected from individuals that are organized into variables, and variables are individual characteristics that are being measured. There are 2 types of variables that we're going to be talking about. The first type is a categorical variable. These values do not have an arithmetic meaning if they're numerical. Often they're just categories or labels. There are no numbers. So for example, male and female would be a categorical variable. You could also assign, let the number 0 represent male, let the number 1 represent female. Well, those numbers don't have an arithmetic meaning, meaning if you do 0 plus 1, well, if 0 just represents male, 1 represents female, it doesn't mean anything when you add them together. So those would be considered categorical variables. Next, quantitative variables take on numerical values that do have an arithmetic meaning. So it could be weight, it could be salary, just any type of variable with a number that if you add the values together or subtract, it actually means something. So that's what arithmetic meaning means. A distribution of a variable are all of the values that the variable takes on. So now let's move to the second page and explore summarizing data with one categorical variable. So for this illustration, consider the data set where we're looking at seasons. Suppose 20 people were asked to identify their favorite season of the year, spring, summer, fall, or winter. Their responses are on the right. So in that table, we see all of the participants listed as well as their responses. So nothing has been done to this data. This would be considered raw data. We haven't summarized it. It's just the data as it came in. Well, one way that we can summarize the data is by using a frequency table. Because imagine that you had 1,000 people in your sample. Well, looking at a list of 1,000 different answers is not going to be very helpful to summarize what was seen. Table is one way that we can do this for categorical data. So we're going to have the possible. Then we can do the count of how many people gave each response. So raw data at the number of people who said that spring was their favorite season, you would see that just one second, having a little technical difficulty here. data, 6 people said that summer was their favorite season, 4 people said fall, and 3 people said winter. So if we total those, we get 20, which is the number in our sample, which is good. Well, we can also use percentages instead of counts. So if we find 7 out of 20, that's going to be 35% of our population who said spring is their favorite season. If we do 6 out of 20, that'll give us 30%. 4 out of 20 is 20%. 3 out of 20 is 15%. And 20 was the number in our sample, so 20 out of 20 means we got our total of 100%. So you can see that this frequency table is a lot easier to view and get a sense of what people in the sample said rather than looking at the raw data. Well, another way that you can visualize or summarize your data is by using a pie chart. So a pie chart emphasizes how the different parts relate to the whole. So we have our whole pie, and we can use the percentages that we found in our frequency table. So the largest percentage was 35%, so that would go in the blue spot, the blue section. And these folks said that spring was their favorite holiday or season. Okay, followed by the red section, where we had 30% who said summer was their favorite season. The gold section, fall, at 20%. And lastly, winter at 15%. So this is another way that you can summarize your categorical data with a pie chart. Okay, well, another way that you can visually display your data is by using a bar chart. So the bar charts emphasize how the categories relate to each other, as opposed to how they relate to the whole, like the pie chart. So for this example, write the appropriate descriptive labels along the axes for the above bar charts. So for the first one, along our x-axis, which is the horizontal axis, that was the favorite season. And then along the y-axis, okay, let's see, for spring, we see that we have a value of 7. For summer, a value of 6. These were the counts, or the number of responses. Okay, well, note that for the bar chart to the right of this one, the general shape is the same. But if you look at your y-axis, the value for spring was 35, for summer was 30, for fall was 20. So remember, that was the percentage of responses. So that would be our descriptive label in this case. For the y-axis, the x-axis would still have a descriptive label of favorite season. And just note, it doesn't matter whether you use the count or the percentage, the shape of your bar graph will be the same when using the same data. Another way that you can visually represent categorical data is by using a pictogram. And so in the Open Learning Initiative, you can take a look at that on page 12. So next, let's look at how we can summarize data with one quantitative variable. So for our data set, we're going to look at some ages. Suppose that the ages of 12 students taking a beginning oil painting class are as follows: So we have a 30-year-old, a 45-year-old, so on, and our last one is 67-year-old. One way that we can summarize this data is by using a histogram. A histogram is similar to a bar chart that we just looked at, and these are the steps to create a histogram. First, we need to divide data into equal bins. Bins are also called intervals or classes. Okay, and we can use interval notation to do that. You can take a look at page 15 in the Open Learning Initiative. I'll also give you a very brief overview when we go through this example. Once we have the bins created, we're going to create a bar graph with the bins along the x-axis and frequency along the y-axis. Okay, so first thing I'm going to do is to define my bins or my intervals. So to help me, before I do that, I should order my data so I can more easily see what is my smallest data value, what's the largest, and get an idea of the intervals that I may want to use. Okay, so I have 19 twice, I have 24, 30, 36, 41, 43, 45, 55, 61, 65, and 67. Okay, so the bins that I'm going to use will be in intervals of 15. So I'm going to draw my axes. Okay, so along the x-axis, this is going to represent the age of the person in the class. So my first interval is going to go from 0 to 15. Okay, then we'll go to 30, so I'm just increasing in increments of 15 to 45 to 60 to 75. Well, to make this more clear, I'm going to write in interval notation what each interval is representing. So in that first bin or interval, I'm going to let this represent all values from 0, including 0, so I use a bracket to denote that, to 15, but I do not include 15, so I use a parenthesis. Okay, so parenthesis means not included. While a bracket means included. So my next interval I'm going to let start at 15, so I use a bracket, and then I'm going to go to 30, but I'm not going to include 30, so I use a parenthesis. So I'm going to follow this pattern. My next bin will be from 30 inclusive to 45 not inclusive. Then I start with 45 inclusive, going to 60 not included, and then from 60 included to 75 not included. Okay. All right, so that will be my x-axis, and my y-axis is going to represent the frequency. So the frequency that we have something in that bin, or in each bin. So somebody aged 0 to 15, we don't have anybody, so that's going to be flat, nothing goes there. However, when we go from 15 to 30, not including 30, okay, we have 3. Okay, so let me mark off, and make sure that you use the same evenly spaced tick marks on your axes. So I'm going to go in increments of 1 up to 5. All right, so we have 3. So the way that we draw the bar is we're going to go up to 3, Then we're going to come across horizontally and go down at the end of that interval. Okay, next we're looking between 30, including 30, to 45, but not including 45. So it looks like we have 4 participants in that bin. So at 30, we're going to go up to 4, come across at 45, and come back down. So next, looking between 45, inclusive, going to 60, not including, we have 2. So at 45, I go up to 2, come across, back down at 60, and then we're going from 60, including it, all the way up to 75, not included, and we have 3 that are in that category. Okay, so we'll go up to 3, across, and back down in that last interval. Okay, so this is another way, or this is a way to represent quantitative data using a histogram. Next, we want to talk about the shape of a graph. So a graph is said to be skewed right if the tail goes to the right. Okay, so for example, if you had a graph with a shape, something like this is considered skewed to the right. So we see that most of the values happen where there's a peak, so most of the values are actually small. There are fewer values that are larger as you go on to the right. Okay, so most of the values are small. Well, if we have something that's skewed to the right, there's going to be something that's also skewed to the left. So something that's skewed to the left may look something like this. So the graph's tail is what will be going to the left if it's skewed to the left, and most of the values happen where the peak is, and we see that that is larger. Another way that we can represent quantitative data is by using a stem plot. With a stem plot or a histogram or a bar chart, you would be able to tell if your data is skewed left or right just by the shape of looking at it. So let's go through how to create a stem plot. So first we want to identify the stem, and the stem is all except the rightmost digit. All except the rightmost digit. So 3, 4, 5 of 55, the 6 and 61, the 6 and 65, all of those numbers would be part of the stem. The leaf is going to be the final digit in each number. Okay, so we want to write the stems in a vertical column with the smallest number at the top. Then we're going to draw a vertical line to the right of the stems. Okay, so why don't we go ahead and let me start this, because I think seeing it will make more sense for you. So I see that for my stems, I'm going to have the number 1 from the 19, 2 from the 24, 3 from the 30, 4 from the 45, 5 from the 55, and then 6. And now I need to draw a vertical line. All right, so that's my stem. So now, to get the leaves, I'm looking at the rightmost digit. So starting with the values that have a 1 in the tens place, we have 2 of them. So we have 19, so we just draw the 9 here. And we have another 19, so we draw another 9. Now let's go down to 2. Okay, so looking for numbers that have 2 in the tens place, we have 24. So we draw the 4, and that's all that we have there. Going down to the 30s, we have 30, so we put a 0, and we have a 36, so 6 would come next. Going to the 40s, we have a 45. We also have a 43 and a 41. Now, although you do not have to write the numbers in order, it just makes it easier to look at, to see that everything is ascending. So I would suggest that you write it in order. So 41, 43, and 45. For the 50s, we have 55. And for the 60s, we have 61, 65, and 67. So we write the 1, the 5, and the 7. All right. So this is an example of a stem plot being used to illustrate your data. There's also something called a dot plot that is similar, and I'll leave that for you to look at in the Open Learning Initiative. We're going to be interested in describing the measure of center of our data, what's in the middle of our data. So we have some more terms that you need to be familiar with. The data value that occurs most often is called the mode. Note that we can have no mode or we can have multiple modes. The average of all of the data values that you have is called the mean. Probably deal with this more than any other statistical value. If n is odd, the median of your data is going to be the number in the middle of your ordered data set. So you number your data set either from biggest to smallest or smallest to largest. The number in the middle is the median. So the number in the middle of an ordered data set. Again, ordered because the values cannot just be random. They have to be from smallest to largest or vice versa. Okay, well, what happens if you have an even number of data? In this case, the median will be the average of the two numbers in the middle of the ordered data set. Okay, well, going back to the idea of skewed right and skewed left. If something is skewed right, then there's a certain relationship that exists between the mean and the median of that data. Okay, so remember, skewed right means the tail is going to be going to the right. So the mean, when you find the average, is going to be affected, even though you only have a few values that are very large, those are really going to pull up the value of our mean, those outliers. So the median, however, is going to be the value that's in the middle of all of our data. So that's going to be somewhere over here. So when we have something that's skewed right, the mean is going to be bigger than the median. Okay, we'll have just the opposite when something is skewed to the left. We see that we have a lot of larger values. However, we have some small values that will pull the mean down. So the median is going to be closer to where most of the values are, the larger values. So in this case, the mean will be less than the median. Well, if we have something with a uniform distribution, just like the name implies, uniform distribution will imply that the mean and the median are the same. So your data would be something like a flat line, just very consistent all the way across.